Okay, welcome to Co-21C, not the 21C. I guess we should go over a few logistical things. But really, I mean, the general idea. So all your faces look relatively new to me. I don't think I see anyone who I saw last quarter. Not that you might not have attended on Zoom, but I see new faces. Welcome. I'm James, by the way. As far as this class goes, it's really just an opportunity to see more examples and do more math. That said, it can be very, what's the word I'm looking for? Interactive, maybe, but more like curated to what you want. So there's a lot of different 21C classes. I imagine many of you are probably in different classes, totally fine. But if there are things happening in your class that you really want to see, I'm happy to make that happen. You just have to let me know. You can send me an email, you can write a discussion post, whatever you want. You can talk to me in person, whatever you want. If you let me know what you want to see, I can do a better job of making that happen. Yeah, and I might, we'll see. I'm considering instituting something I was doing a few quarters ago where I had students do like a weekly kind of reflection / let me know what's going on in your class, because that way I can better know what's going on in your class. We'll see how that goes. I haven't decided yet if that's how we're going to do it or not. What else? Let's look at Canvas for just a minute, just so you can all see things. Come on in, welcome. So Canvas, Co-21C. I guess I have to look up here. So there's a whole syllabus you could read if you felt like it. There's a lot of just whatever information on there that you probably are familiar with already. How to get a hold of me, how to make an appointment with me, when and where you can find me for office hours, stuff about this class, which is just kind of boilerplate. Yeah. You need accommodations. I mean, if you need accommodation, I think I got an accommodation for one person, totally fine. There's not really much to accommodate in this class because there's no tests or homework or anything. So, but I will, if there are needs to be met, I will certainly meet them. Zoom, you're all here in person. No one is on Zoom currently. You are welcome to attend via Zoom. That said, I encourage in-person attendance because I don't know. It's probably my own personal bias that I attended my classes as a student in person. I feel like it's a more interactive way to do things, but whatever you like, it's good for me, it's good for you. And then as far as, so unlike, were any of you in the 21B workshop last quarter? It's fine if you were not, I'm just curious. Great. I don't have to talk about how it's different this time. At least not yet. So some of you may have registered for this class via schedule builder, right? That's how, yeah. And some of you may have just signed up via a Google form to be added to the Canvas. Both ways are fine. Doesn't matter to me really. That said, if you are registered for the class via schedule builder, that means you are enrolled for one workload unit. And to quote unquote pass the class, you have to attend regularly. And I think what I said, 75%, that sounds like what I usually say. Did I even say anything really? Amazing. Usually that's the threshold that we're looking for. Just come. But so also attending, you can attend via, like right now, you can attend by coming via Zoom, or you can watch the video of the class later, and that counts too. But whatever way you do it, I need you to fill out the attendance form because that's where we're going to keep track of things. So the attendance form, I have two of the QR codes right here. Not that one, the ones that I laminated. I would encourage you to bookmark the link somewhere on your phone or computer. You can also find it right here. Hopefully we'll go through. Yeah, it looks like this. It's got kind of a different header than the other ones to make it look different. So, and it should say, you're filling it out for either Co-16, Co-17, or Co-21C, that's you. And you'll need to put in your email and your ID number and your name, just like I would write my name as James Parmenter. I really do want your first name first and your last name last, no comma or anything, just because that'll make it easier for me to input it later. And then what class you're attending for, how you attended, and importantly, what date you were attending for. So like if you watched the video of this class, say 3 days from now, I still need you to write this date. as the date, just so that I can go into it later. Because eventually someone in the course will ask me like, what's my attendance look like? And I'll try to have kept it up to date so you can see that pretty easily in Canvas. If you're not registered for the class, if you just signed up via the Google form, you don't need to be concerned about your attendance, right? Like it doesn't matter at all, except that I still want you to fill out the form because we track attendance also for other purposes, mostly to justify funding. So the more attendance we can show that we have had, the better it looks too. Okay, what's that? There's some student council, I don't know what they're called at the moment. COSAF, I think. I don't remember what it stands for, but it's like Council of Student Services and Fees, maybe, where they ask us to like present to them every year and be like, what do you do with our money? Great. So please do that every time you attend or watch or whatever, make my life easier. So please do it for me. I know you don't know me that well yet, but I'm a nice guy. So you can do it, please. Yeah, I guess the other thing to say about that is to do it in a timely fashion. So I know, and I know it feels like not a hard thing to do, but it feels also like kind of a pain in the butt. Like I have to go fill out the form. I know it's kind of, I feel that way when I have to go enter the attendance. I'm like, oh, I need to do this thing. All right, it's lame, but I will do it. And then places to get more math help, office hours, Grant's website, I will refer to often. It is a very useful resource for any math class. Specifically, here's the link to his 21C class. Lots of handouts that are very useful that I often refer to and use as a source of information. What else? There's our tutoring website, which has just the usual sort of information on it about all the math classes and tutoring and drop-in. And you can help each other. You should get to know each other, right? You're all here. You might not, well, I should think, you might not be in the same math classes. So let me ask, if you don't mind, I might try to learn your names as well. I should do that. What's your name? Caitlin, and whose class are you in? Or do you, who? Alameda, okay. What's your name? Madison, and whose class are you in? Say that one more time. Casals, I don't know who that is. And you? Ashim? Sorry, I also don't hear very well sometimes.
Nosheen.
Nosheen?
Yeah, Nosheen with a pen.
She, great. And whose class are you in? Cool. And how about you?
This.
Or it's nice to meet you, and so nice to meet you both. Not to meet you. And who's class are you in? All right. And lastly, Maggie?
Yeah.
And who's class are you in? Okay, so all four of you are in Casals? And you're in Alameda? Okay, so you're the odd man. Sorry, I imagine there's a lot more students enrolled in this class than there are here currently. A lot of them had time conflicts, so they're going to watch the videos some of the days. That's totally fine if that's you as well. But certainly I would encourage you to use each other as support, as help. That's how I got through the 21 series when I was a student here many years ago, was by studying with other students and talking to each other about the math. What else? You can also make an individual appointment with me if you want to. Yeah. So this page, whatever, you can look at it once or twice. It will probably after this week not be the first page you see if you go into Canvas. I will change the home page to I just clicked on the wrong thing. It's just to take me back to here. I will change the home page to the modules because the modules is really where I think all the useful information is. You're seeing my version of it. So anything that's whatever crossed out, I don't know, what do you call that symbol? It's like the don't do it symbol, the whatever. The denied symbol, anything here you won't actually see on your Canvas because this is the teacher view, not the student view. I guess I could go to the student view. Maybe. Sure, here's what Canvas looks like for you. There's a link to the attendance form, the one we just talked about. There's a link to the Zoom if you need it. My office hours, the 21C playlist that I will add videos to this quarter and also has videos from the last time I taught it, which will probably be similar. The class notes also, which I will be writing in this space here, and then I will be posting later. So you can certainly look at the class notes later, look at the video later for something that you didn't see or you missed and you want to go clarify it for yourself. That's an option. Grant's website again, Kuba's website also, he's a former UC Davis instructor who was one of my teachers and was working here until just a couple years ago. His notes are really great. He's got lots of very useful information. If you're looking for extra homework, which I know everyone is looking for, but really some professors don't assign homework. And so if you're looking for like problems to do that might be helpful and you don't have any other kind of source of assignment, that's a good place to go. I'm also just useful handouts that kind of he draws really good pictures. So if you're looking for more good, so I will say my picture drawing has gotten a lot better over the years. It's still not excellent when it comes to 3D drawing, and we will be doing some 3D drawings in the second half of the quarter. So I will try to refer you to other good pictures. Grant also draws great pictures. So if you're looking for good notes with good pictures, also the book. There's a couple sources. Here are some video lessons we all posted a couple years ago. My website, which really doesn't have much useful information on it. Some stuff from 21B, which may or may not actually be particularly useful. Some stuff for 21C, which is more useful. And then, yeah, exam prep material. So I do also post the recordings here, so you can either find them on YouTube or you can just go straight to Canvas and find the recordings down there, as well as the notes. And then here's all the old class recordings as well. And I think that's about it. Lots of old, I don't know if I really need to have all of those there, but they're at the bottom, so they won't get in your way if you're looking for other stuff. Okay, I think that's most of what I have to say as far as the logistics of the class and Canvas. Oh, I guess I could show you. So I will point out, let's look at the YouTube link just real quick. Can I find it? Maybe. There we go. Yeah, okay, open it in a new tab. Yes, thank you. Takes a moment. So here you can see the videos. They should be sorted as the most recent one first. So here you can see the last time I taught Co-21C was spring of 2022. And if you want to watch old videos of me teaching the class, you can. I don't know if that's particularly useful, but if you want to get ahead, you're like, oh, I want information about this and we haven't done it in class yet, you could look here and find something. And I think they're not super well labeled, which they just have dates on them, which is kind of unfortunate. My plan for this quarter is to actually label them. So in the label, you can actually see the subject matter as well, which I have been doing in the last quarter because I noticed when I looked, like, oh, you can't actually see anything but a date. So the new ones will be labeled better so you can see what the information is actually about. That clock right? No, not at all. Okay. An hour behind, which I guess makes sense. So having said that, I think that is all the logistical things I believe I need to cover. Probably. The big thing really is just fill out the attendance form. As if there's anything you caught from all the stuff I was saying, fill out the attendance form when you come to class. Do you have any questions? Let's see if I remember any names. No, Sheen with an N. Maggie. Lourdes. Crystal? No. Just remind me. Mads, I was like, I think it's an M, but I don't really think it's an M. And you were first, which means I forgot it because it was the longest to go. Remind me. Caitlin, Madison, Maggie, Lourdes, Sheen. Awesome. I will try to remember your names. It'll take some practice. I'm James, by the way. I was a student here many years ago. I took a lot of these classes. I still have a lot of, I was just looking the other day, I was trying to help a student with 22B. I was like, oh, I have an old midterm from the same professor who taught it, who's teaching it to you. The exams look very different. It's kind of interesting how the differential equation stuff really kind of seems to have evolved over the last number of years. So anyway, I guess if you don't have any questions, we can start talking. So who's had class already today? So everyone in, what's the name of the teacher? Alameda? Casales, you're in Alameda. Okay. And you have not had class yet today? Cool. All right. Did they talk about anything in class mathematical, or was it more just kind of how the class is going to work kind of stuff? Okay. Sure. Yeah, that's not, I understand why so eventually the stuff we are doing right now is going to lead to eventually being able to do that. That's kind of why we're going to talk about sequences, which is just a list of numbers in order, and series or summations, which is just adding up those numbers in order. But there's kind of a lot of machinery we have to build up before we get to the place where we talk about approximating functions with polynomials. But it's kind of cool. In fact, since we're here, we might as well kind of talk about that because I do think it's kind of neat. Let's look at just a real quick example. So here's where we're eventually going. For some reasons, it's really useful to be able to do what your professor was talking about, to be able to approximate functions using polynomials. Because sometimes we want to integrate something and it doesn't have an antiderivative like e to the x squared. And if we can approximate that with a polynomial, we can certainly integrate the polynomial. So that's just one reason why you might want to do the thing we're talking about. But let me show you just because I think it looks really neat and really kind of makes me believe how this actually works. So well, this looks, for some reason, Desmos looks different to me than it usually does. Maybe that's just me. So let me just show you real quick. We can totally approximate y equals e to the x with polynomials. So the first, it's going to start off kind of lame. Okay, that's not a very good approximation. It's good right at 0 and not really anywhere else. But then if you start making it better, that's a slightly better approximation. And then if we make it even better, oops, don't do that mistake though. It's even better. And if you keep adding on the subsequent terms of the Taylor polynomial, which is the thing we're actually talking about here, you get a better and better approximation. And it's a better approximation further and further away from where you're actually having the point of approximating. So the idea is you can keep adding on higher and higher order terms of your Taylor polynomial to make this thing look better, look like a closer approximation to the actual curve further and further out. So if you went on literally forever, right, x to the 5th or whatever, x to the 6th or whatever, all the way to x to the whatever over whatever, this would look exactly like e to the x. But of course, you can't actually do it forever. So, right, that's kind of the issue here. So that's where we're going with all what we're about to do. And that's going to pretty much take up, I think, like the first, I don't know, 4 or 5 weeks of the quarter. Maybe not. I don't remember actually what the syllabus looks like. So it might not be quite that much time, but that's what we're going to be doing for the first half-ish of the quarter. And then the second half, we're going to totally switch gears and start talking about kind of 3D stuff, vectors, how to find distances between points and planes, or lines and planes, or points and lines, and kind of other 3D-ish things. I would say lastly, not last, I'm going to say all kinds of things all the time. I a lot of times say, okay, one more example. And then I'm like, well, really, one more example. And really, it's always just, there's always one more example until we run out of time. That's the real truth. I should definitely fix that clock because I'm going to look at it in the time. It's going to be long and reach. That's all. That's all. Let's see what time it is. 10:19. So though, what was that? No, not like that. Maybe I should just kind of. All right. Oh, what I was going to say is that. So I know the last couple of quarters, essentially 21A we covered differentiation and lots of other ways of using differentiation. 21B integration and lots of kind of applications of that. And then 21C, we're certainly going to use differentiation quite a bit. Integration, somewhat. There's not, I mean, it's not like we're just going to be doing integrals and integrals and integrals. There, eventually, we're going to get to a point with series where we talk about the integral test, which will allow us to kind of see if something does a thing using integration. And then other than that, we're going to talk about kind of just how to use these Taylor polynomials eventually to integrate a function or an approximation of a function. But there's not a lot of using all of the things we do. I mean, it's kind of a lie, or not entirely the truth. We're going to be doing differentiating, integrating, just not as much as we were. So, which is kind of too bad because we just learned all the differentiating, integrating. Now it's kind of like, okay, we're going to forget about that for a little while, and eventually we'll come back around to it. So let me organize myself just a little bit here. There's never enough room for this desk. Get some papers. Yeah. Is the is that fairly visible? Like it's not too bright, not too dark. It's always a challenge in this room, especially when the sun, it's actually less of a challenge now than it was a couple weeks ago. Because the sun, is tilting more that way than this way, but still a little bit of a challenge. So let's see. What else to say? If I get off the screen, let me know. I don't always see what's up there because I don't have it over here. I guess no, it really doesn't work to have it over here. I'm really just gonna be looking down here. So just say, hey, James, you're off. No, you can call me James. If you don't, that's not comfortable. I totally understand. You can call me Mr. Parmenter, which feels a lot to say. You can call me teacher, or I'm not a professor, but people like to say that, so you can call me that if that's what's most comfortable. Whatever you like, really, totally fine with me. Caitlin, Madison, Maggie, Lourdes. All right, I think I'm gonna remember your names. Let's see. We'll see on Wednesday if I really remember your names. Okay. Co-21C. Today is what? Oh yeah, April 3rd, right? And let me grab. Feel had a nice, somewhat relaxing break. Got to refresh, energize yourself, not study for a week, I hope. Yeah. Okay, so sequences. A sequence, just a list of numbers. So just list of numbers in order. Unlike, say, a set where you just have some set of things, it doesn't matter what the order is. For a sequence, the order totally matters. And usually the way we write a sequence is by kind of writing the formula for it. So for example, we could write a sub n is equal to 2n over n plus 1. And then we could write out terms if we wanted to. So we could say the terms are going to be, well, if I plug in n equal to 1, and I'll just start there. So, right, if I plug in n equal to 1, I'm going to get 2 over 2. And that's my a sub 1. And then if I plug in n equal to 2, I'm going to get 4 over 3. And that's my a sub 2. If I plug in n equal to 3, I'm going to get 6 over 4. That's my a sub 3. And so on, right? If I plug in n equal to 4, I'm going to get 8 over 5. That's my a sub 4. And you could go on and on and on, right? You could plug in n equal to 100 and get 200 over 101. That would be your a sub 100. And plug in 101. And it just goes on and on, right? That's what a sequence does. It doesn't stop. It keeps doing its thing. It's kind of like a function, except that with a function where you can input any number, right? Like you can plug in a half or a third or pi or whatever. Typically for sequences, the input can only be a positive integer. I should take that back a little bit. It can really be only an integer. Usually we start at 0 or 1, but you could actually start anywhere you wanted to. But you're really only plugging in whole numbers or integers. The question we often like to ask about a sequence is, does it converge or diverge? And all that really means is, does the limit exist or does the limit not exist? So converging means the limit exists. Diverging means the limit does not exist. Well, I know it's been, I should say the limit as n goes to what? Well, we're letting n go on and on and on here. It's always the limit as n goes to infinity. So what's the limit as n goes to infinity of 2n over n plus 1? Well, we've seen this sort of thing. It's been a little while, but we've seen this type of thing in 21A. There's a couple ways to attack this kind of limit. But first of all, if I just think about plugging in, right? You're actually not plugging in, but if you plug in n equal to infinity, you're going to get infinity over infinity. So you could say, okay, this is an infinity over infinity type, which you could either use L'Hopital's rule for, or you could just use kind of the method that you probably learned at the beginning of 21A, which is that if you have a limit of something where the highest degree on the top and the bottom is the same, the limit is the quotient of the leading coefficients. This is just going to end up equaling two, which is just. I didn't actually use L'Hopital's rule, although it might look like I did, right? Because you could say that the derivative of 2n is 2 and the derivative of n plus 1 is 1. But what I actually did was I looked at the coefficients. 2 over 1. It's kind of the same way. This is just like how the limit as n goes to, sorry, I was going to say x actually. As x goes to infinity of 2x to the 6th plus 4x cubed plus 5x plus 1 over 7x to the 6th plus 5x to the 4th plus 3x squared minus 9. That limit is definitely 2/7. Sure, you could use L'Hopital's rule 6 times. We don't want to do that. It's totally fine to say, I know that since the highest powers are the same, the limit is just 2 over 7. And I would encourage you to take that to heart because it comes up often. So back to this one just for a second. So as far as the sequence is concerned, we would say that this sequence converges. So an equal to 2n over n plus 1 converges to 2. You don't actually need to write that down when you're doing a problem like this, but that is the language that we use. It's totally fine to just say the limit's equal to 2, and everyone knows that we mean that the sequence converges to 2 when we say that the limit is 2. But that's probably what people will say is, oh yeah, it converges. What does it converge to? It converges to 2. Let's look at some more examples. Let's say, I'm always going to do that. Also, if you need me to like keep something on the screen so you can see a little bit longer, totally happy to do so. I usually try to do kind of like this, but I'm not good at it. You think I would have had enough practice by now, but it's always like feeling like I'm off screen. Anyway, let's look at some more examples. Let's say we've got a sub n equal to 3n squared over n plus 4. And again, we could start writing out some terms. My first term would be, let's see, so I plug in n equal to 1, I get 3 over 5. I plug in n equal to 2, I get 3 times 4, which is 12 over 6. Plug in n equal to 3, I get 3 times 9 over 7. And I mean, it feels not super important to write out a bunch of terms. You can. I don't feel like it gets you a lot. One thing I will point out is that it's typically not necessary to simplify these things. Yeah, I know 12 over 6 is 2. I'm not going to change it. I'm going to leave it as 12 over 6. And then, yeah, it goes on and on and on. Just to get the notation here, right? This is your a sub 1, your a sub 2, your a sub 3. And it looks like things are kind of getting bigger, right? 3/5, 12 over 6 is 2, 27 over 7 is almost 4, which seems not surprising because the degree on top here is larger than the degree on the bottom. So if we were to look at the convergence or divergence here, well, the limit as n goes to infinity of 3n squared over n plus 4, you could either use the rule that if you have a higher degree on top, the thing's going to go to infinity. But you could also use L'Hopital's rule here. If we use one iteration of L'Hopital's rule, the limit as n goes to infinity of the derivative of 3n squared is 6n. The derivative of n plus 4 is 1. So that limit's going to be infinity. So what does that actually mean? Does the sequence converge or diverge? Well, the better question to ask here is, does this limit exist? And even though we're saying the limit's infinity, that still means the limit doesn't exist because the sequence isn't getting close to any particular number. It's just getting larger and larger and larger. We say it's infinity because it's convenient to say that. It's giving more information than just saying the limit doesn't exist. But really, when we write this down here, this is just saying, oh yeah, the limit does not exist. And I'm being more specific, right? I know it seems kind of strange. Like, James, you just said it was infinity. I did, but I'm saying that also means limit doesn't exist. We're just being more helpful to the reader about how the limit doesn't exist. This sequence is just getting larger and larger and larger, but it's not getting close to any certain number. So this limit does not exist, which means the sequence an equal to 3n squared over n plus 4 diverges. Now, let me ask you all, do you have homework assigned in your class? Caitlin? Yeah, it's okay if you don't know. Do you all know? Okay. So here's what I'll say. I've seen for 21C in the past, or classes where you have to talk about sequences converging or diverging in general, that sometimes they'll just ask you if the sequence converges or diverges, but sometimes they'll ask you if it converges, what it converges to, and if it diverges, does it diverge to infinity or to negative infinity or to a we don't know, it's just not existing kind of thing. And in this case, we could be slightly more informational and say, okay, this sequence diverges to infinity. But often you won't be asked that. So I just wanted to let you know. In fact, let's look at another example that does kind of the opposite thing. Or not the opposite, but doesn't do the same thing. So let's say we want to look at the sequence. A sub n is the typical name for a sequence, but you could actually call it any letter sub n you wanted to. So for example, if I want to change it up and say b sub n equal to, let's say it's -1 to the n plus 1 times 2n over n plus 1. So this is a lot like our first sequence, except now this -1 to the n plus 1 is going to make it alternate signs. So when I start writing out terms, my first term, b sub 1, is going to be, let's see, if I plug in 1, I get -1 squared, so it's going to be positive, and it's going to be still 2 over 2. And then the next term is going to be -4 over 3, because when I plug in n equal to 2, -1 to the 2 plus 1 is -1 cubed, which is going to give me a -1. So this -1 to the n plus 1 means the sign is going to change every term. And then the next term is going to be 6 over 4, and then -8 over 5, and then positive 10 over 6, and -12 over 7, and it just goes on and on and on. So this certainly doesn't seem like it's converging. In fact, we can see that every odd term, so b sub 1, b sub 3, b sub 5, etc., which are all positive, those are going closer to +2, right? Because literally it's the same sequence as the first one, except we've added in this alternating piece. But then every even term, well, b sub 2, b sub 4, b sub 6, they're all negative. -4 thirds, -8 fifths, -12 sevenths. They're getting closer and closer to -2. But if the terms don't all go towards the same number, then the limit doesn't exist. Right? For a limit to exist, the sequence has to get closer to one and only one finite number. So here, if we tried to take the limit as n goes to infinity of -1 to the n plus 1 times 2n over n plus 1, you can't say the limit's plus or minus 2. We have to say the limit does not exist. It's kind of bouncing back and forth between positive and -2. So this sequence diverges. So this divergent. Not to infinity, not to negative infinity. It's just doing this kind of oscillating thing, and we just say it diverges. That's all we can say. Also, you're all welcome to ask questions if you have them. I know we're just starting off, so you probably don't have any questions yet. Totally fine if you do, though. But certainly feel free to ask me any sort of clarification. Also, you might have already noticed my handwriting is less than excellent. That is totally fine. But sometimes numbers look like other numbers. My 8s and 5s and 4s all kind of start to look like each other at some point. So if you need clarification about something I've written, also don't hesitate to ask. Also the words, like I know my writing's not perfect. I have accepted that. But if you need me to clarify something, please do ask. And then lastly, if you think I've made a math mistake, which certainly happens, please speak up. I have definitely done something at the top of a page and gotten all the way to the bottom. And then someone's like, hey, James, what about the thing? I'm like, oh man, yeah, I made it smaller. So if you think you see an error, really, really don't hesitate to say something. Most of the time you will probably be right. And I'll be like, oh yeah, I made a dumb addition error, or I forgot a minus sign or something. So yes, I will make mistakes, not on purpose, just sometimes they happen. Feel free to call me out. My feelings will not be hurt. Sure. Let's look at something like this. Time have we got? We end at 10:50. Let's say, oh yeah. Try to number my examples just so they're easy to find later. Sometimes I start to forget towards the end of the class. Let's say we have something like a sub n equal to n squared over 2 to the n. Let's write the terms. I like to write a colon here. So I know I wrote like a semicolon on the other page. If we just start writing out terms, you get 1 over 2, and then 4 over 4, 3 squared over 2 to the third. So let's say they're getting bigger, right? 1/2, and then 1, and then 9/8. But don't let yourself get fooled by the first few terms. We keep going, plug in 4, you're gonna get 4 squared over 2 to the fourth. Oh, we just got smaller again, right? That's 1, which is smaller than 9/8. If we keep going further, 5 squared over 2 to the fifth, 6 squared over 2 to the sixth, 7 squared over 2 to the seventh. Looks like things are getting smaller. Right, my fractions are definitely all after this point less than 1. 25 over 32, yeah. 36 over 64 is almost a little bigger than a half. This is definitely smaller than a half. So it seems like things are getting smaller. Oh, we can totally be smart about this. I was going to do something dumb, not dumb, just something more complicated than necessary, but you can totally use L'Hopital's rule here. Let's take a look and see. So converge or diverge? That is always the question. Not always. It's often the question. In fact, why don't you guys try? Try taking the limit as n goes to infinity of n squared over 2 to the n, which I will point out is definitely an infinity over infinity form. Yeah, that's the one that's going to be fun. If you're using L'Hopital's rule, which I definitely recommend, I imagine the hang-up could potentially be remembering what the derivative of 2 to the n is. So I guess I definitely lied at the beginning of the class. We definitely use derivatives all the time in this class because we're going to be using L'Hopital's rule semi-frequently, at least for these limits. I know I said do it on your own, but I'm impatient. I just want to do it. I wouldn't. So curious. I will, in the past, when this class was not on video, there was a lot more like me being like, you guys do a thing, then walk around and what doing. But that seems less beneficial for the people that might be watching this later. So I'm going to try and, I don't know, find some sort of balance because I do think it's useful to all of you to actually try and do the math on your own. It's good to practice. That's really, in my opinion, I could talk up here, and you will certainly see me talk up here a lot, but I will do my best to not be just talking and talking and talking, because I think, I know I'm not displaying that very well right at this moment, but I think it's better for you all to get a chance to do the things. So let's talk about this problem, even though I just said if you do it, we're going to do it anyway. If we use L'Hopital's rule, limit as n goes to infinity, the derivative of n squared is 2n, and the derivative of 2 to the n is 2 to the n times the natural log of 2. Just like the derivative of 2 to the x is 2 to the x times natural log of 2. Which is still an infinity over infinity form, right? The top is definitely going to infinity. The bottom is definitely going to infinity. So we're going to use L'Hopital's rule again. It is important to write the limit every time. The derivative of 2n is just 2. The derivative of 2 to the n times a constant, because natural log of 2 is just a constant. It's like 0.7. That's going to be, well, the derivative of 2 to the n is 2 to the n times another natural log of 2, and then the other natural log of 2 is still there. But now we can see the top is 2, and the bottom is getting infinitely large. And when you have a constant divided by something that's infinite, that's going to get smaller and smaller and smaller, and the limit's going to be 0. So this definitely converges to 0. Now, the more important thing to see here is that this kind of shows us, right? You could have had n squared, or you could have had n to the 100th power. And if you applied L'Hopital's rule the right number of times, eventually n to the 100th derivative is going to be constant if you do it like 100 times. Whereas the derivative of 2 to the n is just going to keep on being 2 to the n, 2 to the n times another natural log of 2 each time you take its derivative. That kind of shows us that what we can see here is that any exponential functions generate larger numbers eventually than polynomial functions. Or more mathematically stated, essentially what we're saying here is that a to the n goes to infinity much faster than n to some power goes to infinity. Right? A to the n, that's exponential. N to the p, that's polynomial. There's a few caveats here, like your base should be larger than 1, so a should be bigger than 1, and your power should also be bigger than 1, but those are kind of sensible things to say. So yeah, this is always true, no matter how big your polynomial is and how small your exponential function is, the exponential function will always outpace it or outgrow it or whatever you want to say. It's going to beat it in the race to infinity. So if we had flipped this over and said it was 2 to the n over n squared, that limit would be infinity, because then the top thing would be growing much faster than the bottom thing. And that's often the way I kind of think about it, is when you have a fraction, which piece is growing faster? If the top piece is growing faster, that usually means we're going to some sort of infinity. The bottom piece is growing faster, that usually means we're going to end up at 0. Okay, so now for a harder example. We have time? Yeah, we have enough time. So in this sequences and series stuff, we see a lot of factorials. So a sub n equal to, let's say, n factorial over 4 to the n. And in case you don't remember what a factorial is, that's totally fine. I will just remind you all. So recall, n factorial just means n multiplied by every integer less than it. So n factorial is just n times n minus 1 times n minus 2 all the way down to 3 times 2 times. You don't really need to write the 1 because multiplying by 1 doesn't matter, but we should write the 1. So this is a few examples. 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. 1 factorial is just 1. And I will point out, it is important to know that 0 factorial is defined to be 1. Basically, the rules of math that we want to work don't work if we don't have 0 factorial equal 1. It's similar-ish to why 2 to the 0th power or 5 to the 0th power is also equal to 1. It's the same kind of reason. We've set up kind of rules and axioms that where for things to work the way we want them to work, these things have to be true. We'll get more into that maybe some other time. So if we start writing out terms here, well, 1 factorial over 4 to the 1, and then we have 2 factorial over 4 squared, and then we have 3 factorial over 4 cubed, and then we have 4 factorial, which is 24 over 4 to the 4th, which is big. And then we have, let's do one more, 5 factorial, 120. The nice thing about factorials is you can just take the previous one and multiply by the next number. So really all I did was say, oh, 6 times 4 is 24. 24 times 5 is 120. 120 times 6 would be 720, and so on. And then 4 to the 5th is 1024. And so on and so on. The reason I wrote out so many terms here, is just so that you can see, if you see the pattern in the future, 1, 2, 6, 24, 120, that should clue you into, oh, it's probably factorials. Specifically, when I see the number 24 feels like the marker to me, really. If I see the number 24, I'm thinking, oh, there might be factorials in there, because that's just 4 factorial is 24. You don't see 24 in a lot of other ways, I feel like. Anyway, so how to deal with this one? Well, it's kind of a giant pain because, and this is going to be true, unfortunately, throughout the quarter. If you're looking at this limit as n goes to infinity of n factorial over 4 to the n, which is infinity over infinity type, the problem here is that we can't use L'Hopital's rule because you can't take the derivative in a nice way of n factorial or x factorial. It's not a really differentiable function. So instead, we have to do this kind of thing where you write out some terms and then kind of do something tricky. Do we have enough? We don't have enough time. I'm not going to go over it because I'm going to try to be respectful of my students' time. So what I'll say here is that on Wednesday, we'll talk about how we can show that this, I think this diverges to infinity. Well, let me double check just to make sure. Yeah. So I will just say for now, this diverges to infinity, which is going to show us, this shows that n factorial outpaces any sort of exponential. And on Wednesday, we will actually show the work to show how it works, but it's a little messy. All right. Lovely meeting you all. Say your names one more time. Maggie, Lourdes, Madison, Caitlin, Machine, an N at both ends. Cool. Yeah, nice to meet you all. I hope you find this illuminating, and I'll see you all on Wednesday. And I do highly encourage you to come in person, because I like seeing your faces.